you everybody for coming. It's my pleasure to introduce Miya Pavlock McAuliffe on the kicking off the semester with her thesis defense. And Miya graduated from the University of Washington with a Bachelor of Science degree in oceanography, so she's a fellow Husky oceanographer, fine program there. And in her undergrad, she was already involved in research on seafloor mapping and studying the soundscape of Puget Sound up there in Washington. And after graduation, spent a year in the private sector, and eventually made her way here to Moss Landing, coming through the NOAA CCME program, the Center for Coastal and Marine Ecosystems at CSUMB. And when she applied, she wanted to work on the intersection of physical and geological oceanography, which she's certainly done, although maybe more on the physical oceanography side than she originally planned. And what you'll see is that she's really forged her own path in her research. She was originally interested in the effect of storms on the shoreline where the ocean meets the land, and that interest and considering the type of sampling that she needed to resolve those processes led her to a really interesting collaboration with Sean Harrison at USGS, who introduced Miya to the world of automated shoreline imagery and work that he had started at Sunset State Beach, which is the focus of her thesis. So you'll see that her thesis spans a really impressive array of techniques using cutting-edge automated image processing, installation of a water level sensing system and in the field, and also numerical modeling as well. She's attended numerous workshops on image analysis. She's presented her work at USGS in Santa Cruz, at the Naval Research Lab in Mississippi, and will soon be presenting it at the Ocean Sciences meeting in San Diego. And she must have given a really good talk at USGS because they since offered her a job there, and she'll continue working on the interface of physical and geological oceanography. So I'm very excited for all of you to see what Miya has accomplished in her thesis as she presents to you her thesis on drivers of subseasonal to interannual shoreline change at Sunset and State Beach.
Right. Thank you, Tom, for the great introduction. I'm going to dive right into why sandy beaches are important. And I think we all have an idea of this, but we know that we go there for recreation, we hang out on the beach, we also watch beautiful sunsets, and it's just a really great environment for real estate, general aesthetic, and it's very economically important. It's a very economically important environment. But when we get these storm events that happen really rapidly, we have really high waves. Here's an example in 2016. And then we get very rapid sediment transport on the beach and also on dunes behind or sea cliffs behind, and that can threaten these lovely $1 million homes that are located here, and we want to get ahead of that. And here's another example of how storms kind of force management decisions. So we have an example of Stillwell Hall down in Fort Ord that was removed in the early 2000s because storm erosion started to beat the engineering they tried to install and then was kind of eating away at the land this building was on, and it was a multi-million-dollar project, and anything we can do to avoid these kinds of scenarios or become proactive in front of these scenarios will help us in the future, as well as protect people that live on the coast. And into the future, we have this outlook of sea level rise that here we have up until the year 2100, and then a range of sea level rising between about 41 to 159 centimeters regionally in the San Francisco area, which we can think about, reaching out to our area. And as the waters rise, the impact of storms are only really expected to become more damaging to those lovely coastal homes we've seen. And today we're going to be focusing in the Monterey Bay, and we'll think about a lot of effects that the canyon has on our area. And our main study site is Sunset State Beach here in the northern Monterey Bay. And so I'd like to start by talking about what storms look like atmospherically. So here we have Alaska and then the west coast of the United States, and the contours on this map are atmospheric pressures. So In a typical storm during a regular winter, we have a high atmospheric pressure offshore and then a low atmospheric pressure onshore. And then this black line indicates the direction that a general storm will approach, and typically that will hit the Pacific Northwest and then drive waves to approach from the northwest to our area. But if we think about when we have more intense coastal erosion, we can use an El Nino winter in our area, for example, when the atmospheric pressure shifts, and maybe during a general storm we'll have low pressure offshore, high pressure onshore, and then we get this more westward swing of waves approaching our area, specifically in the Monterey Bay. And this has been linked to more anomalous coastal erosion because a lot of beaches that are otherwise protected will become exposed, and the waves have a lot more potential to move sediment off of our shorelines. And if we think about how wave energy affects the shoreline, we're going to be using this kind of top view of a general sandy beach so that I can explain how wave energy drives cross-shore sediment transport. So in the alongshore direction, we'll think about this along the shore of a sandy beach, and the cross-shore position will be on this y-axis. And then here's blue in the water. Well, the water is blue. And this will be seaward, and then this will be landward. And we'll use this a lot today, so just think about, remember these axes. And if we have high waves, say during a general storm at the beginning of winter, our beaches are pretty wide when they're very accreted. And the direction of sand transport is offshore, indicated by the black arrows. And then the result of that is shoreline erosion, so the shoreline moves landward. And then if we think about at the beginning of summer, after winter, our beach will be very eroded. Smaller waves will move sand back onshore, and then the result of that will be an accreted shoreline. So that's general seasonal change. But also, in addition to wave energy, we have to think about where the shoreline started. So I'll take you through a couple different scenarios of, let's say we have consistent wave energy. We'll start with low wave energy, and then over time, if we start with a really eroded beach here, we'll get accretion with low waves until the beach builds into this equilibrium state where we wouldn't expect it to change anymore with low waves. On the other hand, if we're already accreted, then with low waves, we won't really expect any more change. We'll maintain this equilibrium kind of stable state over time. If we have high waves, say at the beginning of the winter, at the end of summer, the beach is really eroded, the waves are bigger, we'll erode to some narrower equilibrium state. But here, if we get more eroded due to higher waves before less high waves, we'll have some accretion until we reach a stable state. So the point here is that wave energy drives shoreline change, but we also have to think about where the shoreline is starting to see kind of where that shoreline will migrate to get into equilibrium, some expected equilibrium state with a given consistent wave energy. So here we have a side view where we're looking at this beach and then a nearshore sandbar. In the summer, we'll have a more wide beach and an accreted shoreline, and then a sandbar that's typically pretty close to shore. And in the winter, we'll have a more eroded shoreline where some sand has moved offshore, and then typically the sandbar moves further away from the shoreline. And again, here's that cross-shore direction that I pointed out in the last figure, well, schematics. And the sandbar is important to consider because it tends to dissipate wave energy. So waves will come into shore and then kind of get tripped up. Maybe some energy will be dissipated, and then potentially we'll have less shoreline erosion in the presence of a sandbar. In addition to wave energy, we should think about which way the waves are coming from and how that will affect how the shoreline is changing. So here we have the Monterey Bay with Santa Cruz up north and Monterey in the south, and the colors are wave heights. So we can think about the red colors being much higher wave energy, and then these blue colors being much lower wave energy. So in the summer, waves tend to approach from the northwest. Then the Santa Cruz headlands here protect this northern Monterey Bay from the incoming wave energy. And we also have a little bit of canyon refraction, which tends to bend the waves toward the shore as they approach from the northwest. And you can see that a little bit in this yellow where it kind of turns in toward shore. But in the winter, and then just to point out the difference in scales here, going from blue to red is 0 to 3 meters of wave height, but in this winter map, we're going from 0 to 7, so the yellow colors in this are much higher than the yellow in here, just to point out the difference in scales. So we have much higher waves coming from the west in the winter, typically, and the canyon refraction due to the Monterey Bay submarine canyon kind of increases as those large waves start to feel the bottom sooner. And then the sheltering by these Santa Cruz headlands is reduced and kind of exposes these beaches up here that would otherwise be protected. In addition to wave energy and direction, well, I guess we could think about longshore sediment transport that results from changes in wave energy and direction. And so here we have our cross-shore direction and our alongshore direction. And when the waves come at an angle to shore, we develop a longshore current, which is represented by this quantity called alongshore radiation stress that depends on wave direction as well as wave energy. So when this value is larger, we'll expect more sand to cruise along the shoreline. And if we think about that from our top view here, if we have consistent wave energy and direction along shore, we'll get sand moving into our little study area and sand moving out. And when those quantities are equal, we won't expect any shoreline change. So when the waves are coming in at an angle consistently along shore, we'll get sand moving along, but that won't ultimately result in any shoreline change. Alternatively, if you have waves coming in and converging in your study site, you would get sand moving in on both ends, and then that result would bring more sand and you would get shoreline accretion. And then when wave directions diverge along shore, sand would leave your study site, and then the result of that would be shoreline erosion. So the overall goal for today is to quantify the coastal response to storms that can be super damaging. And also, so that'll be part one, and we'll use a more observational approach. And then we'll use those observations in the second part with some modeling to test what physical processes are driving shoreline change. And we're kind of thinking in this study area where we have storms coming in and driving high waves and then forcing coastal change. So to start with, I'll tell you about our study site. So Sunset State Beach here in the northern Monterey Bay. There was a camera station set up by Sean Harrison of the USGS, and he basically didn't have any time to deal with the data, so I was looking for a thesis. And I got this data set, which is really awesome, and I've built on it a lot from what he started on. Here we have Sunset State Beach in the cross-shore direction, and then the camera is located at the top of the dune at about 60 meters. And this study site was chosen for its high vantage point, so we could see more of the beach from really up high on top of this dune. And what we know about Sunset State Beach is that it has a pretty nice seasonal signal. So here's our side view again, like I showed you before, where we have the land over here and then the sea over here. And then we'll see the elevation of the beach profile. And first we'll look at the summer profile in blue, where we have a nice wide beach and then a really accreted shoreline. And then that gently slopes into the near shore. But in red, in the winter, we have a much more eroded shoreline. And then a nearshore sandbar that kind of pops out in the data, but it's really difficult to tell what that sandbar is doing because we just have a snapshot in time from the summer and in the winter. And then the shorelines we'll be looking at today are this intersection between the water level and the beach profile. So just keep that in mind as we go forward. So for part one, we're going to quantify the relationship between the shoreline, sandbar, and waves, which is really difficult to observe with more traditional methods. And my first hypothesis is that in the winter, when high waves come through, we'll see shoreline erosion, like in this case, and we might see that happen a lot more quickly than we would with lower waves in the summer, where we would see shoreline accretion. And then also thinking about that equilibrium state where if we have high waves for a long time, maybe we'll get to some stable, more resilient state than otherwise. And then the second hypothesis is that as waves break over the sandbar, that'll kind of act to dissipate that energy and maybe delay shoreline erosion in the winter due to that presence of the sandbar. And part two, we're going to test the drivers of shoreline change. The first hypothesis is that a simple equilibrium shoreline change model will represent the seasonal change we see at Sunset State Beach, as well as what storms do to this certain beach. So we'll see this, we'll expect to see some equilibrium state at some point if waves are consistent. And then the second hypothesis is that the alongshore transport processes will be negligible because I think the shifts in wave energy will win out over the changes in wave direction. So we'll start with part one, and the approach for that was to use this awesome video monitoring station, and I'll show you a video in a second, but to control for water level, we also need water level observations, which we gathered from the NOAA tide gauge, and then to check on that, we also installed a water level sensor up north, which I'll tell you about in a second. And then we also need to know what the waves are doing, so I'll tell you about this cool wave model that predicts wave conditions right outside of our study area. And so here's our camera located on top of the dune. There's two cameras here that are very nicely camouflaged in the brush to avoid scary people. And then our solar panels power it, and it sends data via cloud so that we can pull the data as often as we need to. And this is what the camera sees. So here on the left, we're looking in the cross-shore direction, and then on the right, we're looking in the alongshore. And to give you a sense, that little red circle, to give you a sense of how big this area is, that's me standing in this camera shot, just like trying to be as big as I could. And so to account for objects and images appearing really small when they're far away from you than when they're bigger when they're close to you, we rectified the two camera shots into one orthomosaic, which is just the two images merged together. And then each pixel in this study area is about, well, it's exactly 0.5 meter wide by tall, and the study area is about 600 by 600 meters. And so the pictures I've shown you so far are regular pictures or snapshots, but the products that I use for my study are called time exposure images. So they're the average of all pixels over a period of 10 minutes. And this camera station was set up to capture pictures every half hour during daylight hours. And so what we'll see in this is the alongshore direction here and the cross-shore direction here. And this happens to be from before I cut it to the 600 meters because we get a little bit blurry as the pixels get bigger out here. And here is the beach, and here is the water level. So I'll show you a video from the month of February of 2018. And you can see the water level coming in and out as the shoreline changes every day. And then at low tide, you can start to see this sandbar feature popping out in the near shore as waves trip up and then break there kind of more preferentially than in other areas. So I think it's pretty fun to watch that beach breathing. And I'll just take a break here. And this diagonal line was, at certain points, the two cameras would have different exposures, so you can see that seam every now and then, which was sometimes a problem for shoreline mapping, but sometimes not. So in order to control for water level, to make sure we're not saying the shoreline is changing when it's just the tide changing, I gathered these observations from the NOAA tide gauge, but that's 30 kilometers away, and there could be some shifts in water levels from the southern Monterey Bay to the northern Monterey Bay, maybe due to wind, maybe due to different temperatures. So to test the difference between the water levels down here and up here, I installed this sensor at the end of Seacliff Pier, and it's a nice radar water level sensor that looks down at the water and measures the water level, and is powered by solar panel and then sends data via cellular so that I can get it once an hour every day. And a result of this is that the differences in water level from August to October of last year were less than 5 centimeters, so it's kind of a negligible value, but this is out in monitoring still to see if we'll see anything further. So here's the tide record from the Monterey tide gauge, and we have water level on the Y. And to map shorelines, I chose the mean high water tidal datum and picked all the pictures that corresponded with times that the tidal elevation was at mean high water. And so this will be a video with the Alongshore on the bottom and cross-shore up and down for all the shorelines that were mapped during this period. And so in September of 2017 into the winter, we saw a pretty moderate amount of shoreline erosion occur. And then into the spring and summer of 2018, the shoreline built back out in the summer. And then into the winter of 2018 to 2019, we saw a lot more drastic erosion as sand was moved into the nearshore. And then for sandbar mapping, I chose a water elevation at low tide so that I could get more of that sandbar feature pop out, and then mapped along the shore here, and I'll show you all of the sandbar observations. There's less of them, but you can see the seasonal signal kind of going in and out. Into the spring, the sandbar is pretty close to the beach in the summer, and then in the winter, it got pretty far off. And to get waves, I used the data from the Coastal Data Information Program's Monitoring and Ocean Prediction wave model, which is a spectral refraction model that's based on offshore wave measurements and estimates how the canyon will influence the waves that are coming into the bay. And we have predictions every 200 meters alongshore in the Monterey Bay, and they give us predictions at 15 meters depth, which is just about a kilometer offshore from our study site. And to make sure that model was working, we deployed an ADCP, or an acoustic Doppler current profiler, which measured waves at the same location that this model was predicting wave conditions. And we see wave heights compared from observations and then from the model, and they matched quite well at about a 0.9 R squared value. And this instrument was deployed in December and January of 2017, 2018. And just to point out that waves do mostly approach from this perpendicular or shore normal angle, which is shown in this green line. So when waves are directly approaching the shore, we'll see them come in at shore normal, and then the rest of the waves observed during this time range within about 40 degrees. So to put all of that information together, in the top panel we have cross-shore position. So here we have shoreline position, and then time from September of 2017 up until May of 2019. And in the summertime in 2017, we see a really nice wide beach, and then rapid erosion in the winter, builds back up into the next summer, and then erodes again into the second winter. And then for our sandbar position, we see it kind of more gradually moving offshore into the nearshore, and then reaching this maximum in late winter, early spring, moving back onshore, and then off again in the next winter. On the bottom, we have those wave model estimates for right outside of Sunset State Beach, ranging from 0 to 4, and wave heights during this time were almost always below 2, except for in the winter, 2 meters, except for in the winter. And then we can start thinking about how these storm events or high energy wave events are going to affect the morphology we've observed. So here we see the first onset of high waves or storm in the winter of 2017, 2018, that drove really quick erosion, and then the sandbar was still kind of migrating offshore. In the second winter, we see a lot more storms occur. The first large event drives pretty rapid shoreline erosion, and then that shoreline kind of gets to a stable state with these high waves while the sandbar moves offshore. And so if you notice, in the second year of these sandbar observations, there's not as many observations, and part of that is due to the government shutdown in January, so we didn't get any data here, which was the most exciting part of my study period, so that's okay. And using this wave record, we observed that this 95th percentile of wave heights was required to drive this really rapid shoreline erosion, and that happens to be at about 1.7 meters in our area. And then we also see that a higher average winter wave energy in that second winter drives a lot more erosion on the shoreline than a lower average in the winter. And then if we think about how the sandbar and the shoreline relate to each other, getting at that second hypothesis of if the sandbar protects the shoreline from erosion, we have sandbar position on the X and then shoreline position on the Y. And each dot is a combination of a sandbar and shoreline observation, where the black circles are monthly, just to give you a sense of what the colors are. So we start in September of 2017 in blue and then move into red by May of 2019. And what I want you to focus on in this figure is that the sandbar varies a lot more in the cross-shore direction than the shoreline does, where the sandbar moves back and forth by about 100 meters, and then the shoreline moves back and forth by about 60 meters. And that kind of makes sense because the sandbar is always exposed to waves, where sometimes it might be protecting the shoreline, which will be a lot more difficult to move. And this also points out differences in timing between sandbar and shoreline migration. So the sandbar is pretty gradually moving back and forth seasonally, but the shoreline stays stable for much longer in the summer before it erodes due to those high waves in the winter. And thinking about that equilibrium shoreline response I introduced to you earlier, we're going to consider this wave height squared and then divided by 16 as our wave energy quantity to be consistent with previous studies. And when we put shoreline position on the x-axis, we see a very wide or accreted shoreline on the right and a more eroded shoreline on the left, and then wave energy increasing as we go up. And each point is a shoreline observation that's colored by the shoreline change rate in meters per day. So what pops out here is that these points above an estimated equilibrium state, where if you had consistent waves at a given wave energy, we wouldn't expect any shoreline change if those waves were to continue. So when we have really wide accreted beaches, we're more likely to see erosion. And when we have really accreted narrow beaches, we're more likely to see accretion, where red are up to -2 meters of shoreline change per day. So that's shoreline erosion. And in blue, it's up to 2 meters of accretion per day. And so we'll talk about this a lot more in the second part, but just keep this in mind as I wrap up this first part. And so to put everything together and kind of discuss how the whole system works together, we see as waves increase, that drives really consistent offshore sandbar migration. And up to a certain point, the sandbar gets a certain distance offshore. At the same time that waves come above this 95th percentile. And then we get rapid erosion. And then without any consistent storms during the winter, we see this accretion happen pretty quickly after. It takes a lot longer to accrete than it did to erode. At some point, the waves get small enough and start driving the sandbar back on shore. And then we see a similar scenario happen in the second winter, but with these sustained storms in the winter of 2018 to 2019, the shoreline stays more eroded. But what's important to notice is that it doesn't continually erode with these high waves. It kind of reaches this seemingly stable state as the sandbar is migrating offshore. So to wrap up what we found in part one, the shoreline does depend on wave energy and previous shoreline position, suggesting that equilibrium shoreline response. And then in part 2, it's really difficult to conclude if the sandbar does protect our shoreline because it was migrating offshore at the same time big waves came, and that those positions were different each year. So it's possible that the sandbar delayed that shoreline erosion, but since that happened at different times each year and the waves got bigger, it's really difficult to conclude. So maybe, but maybe not. I'd love to keep monitoring this to see if that is true at sunset. So the second part, we'll talk about the drivers of shoreline change. The first hypothesis is that this simple equilibrium model will work and predict how the shoreline will change. So just considering wave energy, I expect to be able to tell you how the shoreline will change. With the second part, I don't think the alongshore transport processes will cause significant shoreline change. And I expect this kind of scenario where the same amount of sand is entering than is leaving. So no shoreline erosion would occur. So the approach here is to use this nice model using wave energy to see if the shoreline depends on wave energy. And then the second part will be to estimate the amount of shoreline change due to alongshore transport processes to make sure and test that second hypothesis, whether there will be sediment leaving on either side of our study site. And so the model I selected was developed by a study by Yates and others in 2009, and their first study site was in San Diego, and then they later developed their model, or expanded their model in 2011 in San Francisco, and they used over 5 years of data and a much longer alongshore stretch and get this really nice relationship that is suggested by my data. So we have wide beaches over here, narrow beaches over here, and then wave energy increasing up, where these really wide beaches are more likely to erode, and then these really narrow beaches are more likely to accrete. And the equilibrium state they estimated from their data is dependent on shoreline position. So a smaller amount of wave energy is required to maintain a wide beach, where a larger amount of wave energy is required to maintain a narrow beach. And we have these two parameters, the slope and the y-intercept of this equation, to use to tune to our data. And then to estimate the shoreline change rate and then get ultimate shoreline change during our study period, we have the idea of this energy disequilibrium, which is basically how far away any given shoreline observation is from what we would expect it to be at a given wave energy. So like here, we would expect a lot of shoreline change to occur to get to this equilibrium state, where if we were much closer to the line, we wouldn't expect as much shoreline change. And we also have these last two parameters, C, which differ for erosion and accretion to fit with our data. But the point is that the shoreline change rate is going to be proportional to how far out of equilibrium we are at any given time. And to remind you of our data, we do see those more red points pop out up here, and these more narrow points pop out here. So let's say, take this point, for example. We'd expect a lot more shoreline change to occur to get into equilibrium with wave conditions than we would for a point maybe already in equilibrium with waves. And to run our models, we first supply these educated guesses for those parameter values I showed you, then optimize those parameters to minimize this root mean squared error value, which is the difference between our modeled and predicted shoreline observations and modeled positions. And then 3 is to rerun those, that model with those optimal parameters to try and fit that to our data. And to show you, and for some reference, these are the 2 study sites treated by the Yates studies. In San Diego, we have shoreline observations in black and then shoreline predictions in gray. Same thing here in San Francisco, or outside of San Francisco at Ocean Beach. And their root mean squared error value is about 5 meters, so that gives us an idea of a value to shoot for when we test the model at our study site. And so once we've gone through that modeling workflow, we get our modeled shoreline position in black, and here's the cross-shore direction for shoreline again. And then over time, from the beginning of our study site to the end, we have our shoreline observations from the camera station in red, and then the wave energy values in gray. And we see that the model does predict the trend in general, but there's some over-prediction here and under-prediction here. And we get an RMSE value of about 6.4 meters, which is a little bit higher than what Yates got. So are these alongshore processes, alongshore transport processes, affecting how the shoreline is changing? And if we accounted for that in the shoreline model, would that lower our RMSE and then give us a model that's more representative of the system? To quantify the amount of shoreline change due to alongshore sediment transport, we can think about the shoreline change over time being proportional to the amount of sediment that's moving at different points alongshore. And when we quantify the amount of sediment transport, we can think about these black arrows as the quantity going in either direction. The alongshore sediment transport is dependent on alongshore radiation stress, which depends on wave energy and direction, as well as wave speed, and then this empirical constant and additional parameter K, which has been found to be at about 0.6 at a bunch of different study areas around the world, and that's kind of what we end up with. That's approximately what we end up with at sunset as well. So if we think about those sediment transport quantities over time, we're looking at alongshore radiation stress, which is proportional to the amount of sediment transport we would expect to see at Sunset State Beach. And here we have those lower wave energies and high angle wave approaches driving southward sediment transport to the bottom of our y-axis. And then up here, we would have northward sediment transport. And over time, the alongshore radiation stress is colored by wave direction. So the red colors are going to be waves coming from the northwest and driving southward sediment transport. In the first winter, we see southward sediment transport happening along the way. And then these, the red line is from a point north of our study site, and the blue line is from a point south of our study site. So when those lines are very similar and track together, we wouldn't expect any shoreline change or very minimal shoreline change. But in this second winter, we see that these lines get really far apart, and that suggests this kind of scenario where sand is moving out of our study site on both sides, and we might see more shoreline erosion. And then just to give you some reference, these are waves coming directly perpendicular to shore, where we would expect that northern Monterey Bay to be more exposed. And then when we estimate shoreline change due to this alongshore sediment transport, in the first winter, there's not that much. This is shoreline position with erosion coming down. There's not much shoreline erosion in the first winter, where when we get this scenario and we get sand being pushed out of our study site on either bound, there's much more shoreline erosion that occurs. And just to, I guess, make my point, these sediments are moving out of our study site on both sides, and that contributes to more shoreline change. But this is about half of the observed erosion we saw during this winter, which could be pretty significant in our model. And when we start to think about why we got this situation in the second winter and this situation in the first winter, we can look to what offshore waves are doing. And so for the winter of 2017 to 2018, we have low wave energy in light blue and high wave energy in dark blue. And then the circle can be thought of as compass direction, where south is to the bottom and west is to the left. And in the first winter, most of our waves approached from the northwest, and that sheltering by the Santa Cruz headlands was increased, and then not as many waves were refracted by the canyon. And then this black line is that angle perpendicular to shore when we'd expect our beach to be most exposed. In the second winter, from 2018 to 2019, we see this direction of wave approach swing to the south so that the study site becomes more open and the sheltering by the Santa Cruz headlands is reduced, and also the wave refraction would be increased. So it kind of makes sense with why we saw waves coming up this way and then driving shoreline erosion out of our study site. So when we combine those two models, shoreline change due to cross-shore sediment transport in that equilibrium shoreline change idea, with the alongshore sediment transport term due to longshore sediment transport, we get the black line, which is the complete model with both terms, compared to our gray line, which was just the equilibrium response before on top of those shoreline observations. And our RMSE value is reduced to 5.6 meters, which is a little bit closer to the Yates studies, suggesting that alongshore transport processes are, in fact, important to consider at our study site. To summarize what we found in that second section, we found that the shift in offshore wave directions definitely exposes Sunset State Beach and drives increased shoreline erosion. And that's partially due to this equilibrium shoreline response where we have higher wave energies reaching the shoreline. But it's also due to this divergence in sediment transport where the wave directions are refracted by the canyon and then drive sediment transport in to the north and also to the south. And if we start to think about how our 2-year study period shown here, our observations are in black for shoreline position, and some biannual observations are pulled out from my data shown by the red dots. If we extend that back with the surveys we have from Sunset State Beach seasonally, where these gray points are winter months when you have higher wave energies, we see that video monitoring really resolves this higher variability, higher temporal resolution variability, where you can begin to observe what these individual high waves are doing to the shoreline, and we don't necessarily have this linear erosion and accretion. And we see these differing time scales of high waves and low waves and how long erosion and accretion takes. And if we compare the fact that we saw higher winter wave energy occur in the second winter compared to the first winter, and we saw more shoreline erosion in the second winter compared to the first winter, going back, calculating average wave energies from previous years, in the winter of 2015 to 2016, we saw this really high winter wave energy that drove a high magnitude of shoreline erosion. And that was an El Nino year in our area where the waves, the offshore waves kind of swung to the south due to those shifts in storm tracks and drove enhanced erosion. But in this year of 2018 to 2019, it wasn't an El Nino year, but the mechanism is very similar to where we have these storm tracks shift to the south and expose the Monterey Bay, northern Monterey Bay from wave approach. And so generally El Nino years are correlated with high magnitudes of coastal erosion in our area, but potentially if we're thinking about predicting how the shoreline will change in the future, if we could predict how these how these storm tracks were changing, we would have a pretty good idea of the amount of erosion that'll occur, because with the higher average winter wave energy and with that westward wave approach to the shoreline, we get that exposure and refraction that drives increased shoreline erosion due to wave energy, but also due to longshore sediment transport processes. And just a couple quick notes on the limitations of this model. Another observation we get from the longer time series of biannual observations is that the shoreline doesn't necessarily return to the same position each year. And that suggests that when there's a really large shoreline erosion event, it takes some time for that shoreline to get back to where it was before. And that could be because a lot of sand gets moved offshore and then pushed alongshore, and maybe we're getting different quantities of sand coming from the north to refill that beach. And that's not something that our models can account for. So starting to think about the sources of sand and where those are coming from and how that will differ from year to year might improve this performance in addition to understanding how those storm tracks will change in the future. And for a quick management application, in addition to where sand is coming from, we have to think about where the sand is going. And a hot topic in our area right now is this CMX sand mining plant, which takes out tons and tons of sand every year from the southern Monterey Bay. And this has been attributed, or I guess correlated with really high erosion rates south of the sand mining plant. And so I'd like to suggest that we install one of these video monitoring stations to see how this will change over time, because we're still pulling out sand until the end of this year. And we expect really rapid changes to occur when that sand isn't being taken out anymore. And that monitoring a change like this would really inform how both wave energy and direction influences shoreline change. And what the ultimate goal of, at least what I think of as the ultimate goal for my work, is to try and improve future predictions of shoreline change. So if we think about future predictions of wave conditions as well as sea level projections, we can take all the data we have and then try to predict how that will change in the future. And we can use that information to inform these management scenarios, where we have a prediction of overall shoreline change, which depends on the shoreline change due to alongshore sediment transport, as well as shoreline change due to cross-shore sediment transport. And then you can start including terms like sea level rise, as well as kind of the best model fit we can get to match what we've observed in the past. And the point I want to make with this is that video monitoring really resolves a lot more processes that we can use to test our understanding of how these different parameterizations of, say, changes in alongshore transport and cross-shore transport drive shoreline change. And so I think we should put video monitoring stations all over the place and start observing as much as we can in order to inform these future changes, which will likely get a lot worse and a lot more damaging to communities on the coast with sea level rise. And I'd really like to thank so many people for helping me get this project done. I got to work with tons of different institutions throughout the Monterey Bay. Huge thanks to Sean Harrison for responding to an email I sent him out of the blue. It was really amazing to develop that collaboration. Huge thank you to my committee for all of your feedback and support, as well as everyone here at Moss Landing. It's a really great community to be a part of. I also must thank the NOAA Center for Coastal and Marine Ecosystems for making this whole thing possible. I've gotten to do so many things that I wouldn't have otherwise been able to do, so that's been really cool. Thank you to my friends and family, and thank you all for being here today.
Any of the work that's being done with these like remote camera systems be done with satellites, or do they just not have the resolution yet to be able to do good shoreline monitoring?
There's actually, in recent years, been a ton of developments with satellites. It's a lot harder to get sandbar observations because those time exposure images become really important, and the temporal resolution of satellite pictures isn't great enough to average out breaking waves. But there's this really cool tool that was developed in Australia that you can basically take all the satellite images that are available and then give it your bounds of where you want the shoreline to be, and then tell it what calculations you want, and you can get shoreline change rate and shoreline position and everything at the best resolution you have from the satellite products. And I tried that here in Monterey Bay, and it actually worked really well. And I think that that's a great question, and it's definitely being developed. And I think that satellites could help us kind of go back in time also to get a better resolution time series of shoreline change, and that could inform future projections as well. But yeah, it's definitely possible for shoreline mapping. not necessarily sandbars yet.
What would you say is the most important observation you would like to have had at the study?
Well, I think that some more measurements of the bathymetry and the beach slope and more information about maybe the types of breaking waves we would have and how the bottom in the near shore influences how waves change would be really, really cool. So maybe like really high resolution drone surveys or something that could give us more elevations, because sometimes certain features develop at beaches that can affect how waves change. Like for example, from the winter to summer, we can have really low waves where maybe we'll have shoaling waves that don't really drive any offshore sediment transport, and that's why we get this consistent sandbar position. But in the winter, when really high waves occur, we can get the like really strong undertow that pulls sediment offshore at depth. And having an idea of what types of waves those were, as well as like what the bathymetry was to see how those processes relate, would have been really cool. I think that would have helped me a lot with thinking more about what the sandbar was doing. But yeah, I would say that for now. Tons of answers.
I would point out that we maintained two old-fashioned camera systems for about 6 years near Stillwell and Marina. That you know, more you can chew on that.
Sorry if I missed this, but did your camera able to take pictures at night? Because I know sometimes the low tides are at night, so
Yeah.
I'm worried to see sandbar data with that.
Absolutely. That could be a huge reason why I had a lot fewer sandbar observations than shoreline observations. So no, I couldn't with my camera, but there are infrared cameras that can get those observations during the nighttime, which would kind of be a next step to amp up the power of that camera and then get those nighttime measurements.
Just thinking about the winter storm events and I liked your analysis of sort of what type of winter we're having. But I'm curious if you could comment on whether we have one winter where we have one really, really, really large wave event versus a winter with the same mean but lots of smaller events.
Yeah.
What do you think the difference would be?
So in the winter of 2017, we had the highest waves on record observed here. And that does drive the average up, but since it's such an episodic event, it kind of all hits the beach at once and can't work on that sand to get it offshore. And so those really quick events, I don't think will have as big of an influence as those sustained events with higher energy to then pull more sand offshore. And that's suggesting that equilibrium response where higher sustained waves will do more damage than that one quick event. Yeah, thank you.
Does the tonnage of the sand that the cement factory takes away, is it in the same ballpark as the amount that accretes in a year?
I believe that it's more. And that's why we see that those high magnitudes of shoreline erosion south of the study site, because since so much sand is being taken out, it can't build back fast enough to account for that. And I think that's a big reason why the community voted for this sand plant to close, because the system wasn't able to keep up with all the sand that was being taken out. So yeah, no, that would be really interesting to quantify also, because we have ballparks. I think it's greater, but I'd have to double check. Yeah.
I mean, if they stop taking sand, is there going to be a negative effect somewhere?
I don't think so. I
Yeah.
think it'll be all good. I think everybody will be happier, and some hotels might be able to last longer. So, yeah.
Yeah, it's been a real pleasure watching you go through this process for a few years. Yeah, and in fact, you reminded me of the beaches that you study. That no matter what you're getting hammered with in terms of challenges, that you always accrete. That's my approach today. But my question for you is, you talked about how it doesn't seem that the beach necessarily always comes all the way back to its equilibrium. And I was wondering, is that related to, or in fact, how relevant is the fact that the beaches that you're looking at are generally backed by cliffs rather than sort of sloping dunes? And the cliffs are much more robust. And when they do get cut back, they don't return.
Right.
And so how is the backing of the actual beach profile, how is that important as to whether it's a dune or a cliff?
Yeah. So when waves get high enough, they could erode a cliff, like you said, and then that sand, it's really hard to develop a cliff. It takes lots and lots and lots and millions of years, right? But when you have a dune, it's sand, and it's also difficult to build back a dune because if you have vegetation, right, that'll hold the sand in place more. But I'm not sure about that. The sand from the dune could actually cause shoreline accretion in the winter, as that if high waves get back to the dune and pull that sand onshore, it could build that shoreline out. But also most of the net transport direction is to the south. So sand coming from cliffs up north and then feeding those beaches to the south could feed them also. But yeah. I think that a dune-backed beach might have more potential to recover than a cliff-backed beach because of those different time scales of building that cliff and that dune. But that's an interesting question. We should talk more about it. That's the best I got right now. Yeah.
One of the big problems with the model is it couldn't keep up with the accretion rates that you saw. Do you have any factor in the model that you can think of that could be the reason why it can't keep up with that?
That could be due to sand coming in different quantities at different times from the north, but I also think it's due to my 2-year study period, under 2-year study period, potentially not being long enough to tune those parameters. So I think that observing this beach for longer would probably tune that accretion parameter a little better. So yeah, longer study period to get better model parameters, but also thinking about the different amounts of sand coming from the north or south or wherever, or cliff or dune. Yeah.